Hey everyone, welcome back to the deep dive. Today, we're plunging right into the very heart of the digital world, Linux. Understanding this foundational operating system isn't just about technical know-how. It's really about unlocking some incredible power and insight. It can genuinely transform how you interact with, well, nearly every piece of modern technology out there. So our mission for this deep dive is basically to act as your shortcut. We want you to become truly well-informed about the core principles and also some of the surprising capabilities detailed in Linux Basics for hackers. We've taken critical excerpts, specifically from the 2019 book by Occupy the Web, published by No Starch Press, and we're here to extract the most important nuggets of knowledge just for you.
And that's precisely what makes this journey so essential. It doesn't matter if you're a seasoned pro or just starting to explore the digital landscape. This deep dive really is an indispensable step for anyone curious about cybersecurity, maybe system administration, or simply gaining a profound understanding of how modern digital infrastructure actually operates. We won't just uncover what Linux can do, but we'll dig deep into why it's structured the way it is. I think that's where those real aha moments happen,
Yeah.
when the complex topics suddenly click into place and you get that comprehensive perspective.
Okay, let's unpack this right from the beginning then. When we look at the whole landscape of operating systems, Windows, Mac OS, why is Linux, of all choices, the undeniable preferred option for hackers and security professionals? It feels like there's some kind of fundamental alignment happening there, something about its very nature that just makes it uniquely suitable.
Yeah, what's truly fascinating here is exactly that inherent alignment you mentioned. Linux's core design philosophy, it inherently supports the kind of deep system interaction and granular control that is absolutely crucial for these specialized fields. It really boils down to a few key pillars that set it apart.
Okay.
First, and well, arguably most profoundly, Linux is open source. And this isn't just some buzzword about free software, right? It's really about transparency and control. Unlike proprietary systems, maybe like Windows, where the inner workings are on a closely guarded secret, Linux's entire source code is openly available. Anyone can look at it. The profound implication here is that you can inspect it, you can modify it, you can manipulate the operating system basically however you please.
Which sounds incredibly powerful.
It is. For security professionals, this means they can scrutinize every single line of code for potential vulnerabilities or, understand exactly how a system will behave under very specific conditions. And for those aiming to make a system behave in ways it wasn't originally intended to, maybe for security testing, maybe advanced customization, being able to manipulate that source code is just essential. You're not just a user anymore, you're a potential architect, maybe even a re-engineer of the system. This transparency, as the source material emphasizes, it shines a spotlight directly on each and every component. And that's critical for effective hacking or, conversely, system hardening.
Okay, so transparency is number one. What else?
Well, this transparency directly enables what we call granular control. Linux provides the book says, almost infinite amount of control over the system, from the tiniest details to the big macro-level functions. And crucially, all of this is controllable directly via the terminal, the command line.
Right, not hidden behind graphical menus.
Exactly. That contrasts really sharply with Windows, where your control is often limited to what Microsoft decides to expose through those GUIs or maybe some constrained APIs. This deep granular control isn't just about tweaking settings either. It means you can, say, fine-tune your network packets to try to evade detection or orchestrate really complex attack sequences with a precision that's simply impossible on more locked-down systems. It's kind of the difference between just driving a car and being able to rebuild its engine while you're still in the race.
That's a great analogy.
And this level of fine-tuning, it inherently simplifies and makes the whole process of scripting more effective, which we'll definitely explore later on.
Okay. Transparency control. What's the third pillar?
Another really compelling reason for Linux's dominance in this sphere is just the sheer volume of specialized tools available for it. The book states that well over 90% of all hacking tools are actually developed for Linux first.
Wow, over 90%.
Yeah. I mean, there are a few exceptions, tools like Cain Enable or Wicto for Windows, but these exceptions really just prove the rule. Even when powerful tools like, say, Metasploit or Nmap are ported over to Windows, they often lose significant capabilities or functionality in the process. It just makes the Linux versions inherently superior for advanced operations. This whole ecosystem of tools becomes this self-reinforcing cycle, you see. Because Linux offers the control and transparency needed, developers build for it. which in turn attracts more users who need those tools. The author even makes a pretty strong assertion that the future belongs to Linux Unix, pointing to Microsoft's slowing growth compared to the expansive footprint of Linux systems across, well, all sorts of technology domains.
That's a powerful set of reasons right there, really defining its place. And, when we talk about Linux in the context of cybersecurity, one name almost always seems to come up, Kali Linux. What makes this specific distribution so special? Is it just a big collection of tools, or is there more to its design than that?
Yeah, Kali Linux isn't just any Linux distribution. It was specifically designed for penetration testers and hackers by a company called Offensive Security. It's actually built on Debian, which is a highly regarded and incredibly stable Linux distribution in its own right. Now, while there are many different Linux distributions out there, you hear names like Red Hat, CentOS, Mint, Arch, SES. They all share the same foundational Linux kernel.
The core engine, essentially.
Exactly, the very heart of the operating system controlling things like the CPU and RAM. But they differ in their specific utilities, the applications they bundle, and often their graphical interfaces like Gnome or KDE. This means each distribution looks and feels a bit different and is often tailored for different purposes. The practical benefit of Kali's design, particularly for its target audience, is just immense. It comes with a significant complement of hacking tools pre-installed, hundreds of them.
So it saves a lot of setup time.
Exactly. It saves users hours of setup time that they would otherwise spend downloading and configuring each individual tool. You can basically hit the ground running. Just for context, the source material we're drawing from specifically references Kali 2018-2, which was the latest version when the book was written.
Okay, this raises a really important question, especially for anyone just starting out. If you're a beginner, how do you even get this powerful operating system onto your machine without the risk of potentially breaking everything else you already have installed? That can feel like a pretty daunting first step.
Well, that's a very valid concern. And it's exactly where the concept of a virtual machine becomes not just convenient, but actually highly recommended, especially for beginners. Installing Kali into a VM or virtual machine is really the best solution for learning and practicing. Why? Because it creates a completely isolated environment.
Like a sandbox.
Precisely. You can experiment, you can break things, you can learn by doing, and then just start over without ever affecting your main operating system, your Windows or Mac OS installation. It's like having a digital sandbox where you can build and destroy castles without any real-world consequence.
Okay, so how does that process work?
The process itself is actually quite straightforward these days. You typically begin by downloading the kalilinux.iso file. Think of it as an exact digital copy of the operating system installation disk. Then use free virtualization software. VirtualBox, a really popular one. Within VirtualBox, you'll create a new virtual machine, point it to that .iso file, and then select the graphical install option. It walks you through the steps in a pretty user-friendly interface.
Are there common hurdles people run into during installation?
Yeah, you might encounter a few common challenges, but they're usually easily overcome. One frequent installation error is the need to enable virtualization support in your computer's BIOS settings. The BIOS is like the low-level startup menu for your computer.
Right.
Since every system's BIOS can be slightly different, a quick online search for your specific machine model, like Enable Virtualization Dell XPS 13 BIOS, should guide you on how to do this. Additionally, if you're installing Kali on a Windows system, you might need to disable any competing virtualization software you have running, like Microsoft's Hyper-V.
Okay.
Again, a simple internet search will typically provide the necessary steps. But rest assured, when it comes to partitioning disks during the installation process,
It always sounds scary.
it does. But selecting the option Guided Use Entire Disk is perfectly safe when you're installing inside a virtual machine environment. This is because you're working with a virtual disk, essentially just a large file on your main hard drive that is new and empty. You're not actually erasing any data on your physical hard drive, so it's a completely risk-free way to get started with Kali.
Okay, so you've successfully got Kali up and running in a virtual machine. That's a huge step. But now what? The book dives right into these foundational terms and commands. It really feels like learning the very language of the system itself.
That's a perfect analogy. If we connect this to the bigger picture, mastering these basics is absolutely like learning your way around a new city.
Yeah.
You need to know the landmarks, you need to understand the street signs, and most importantly, you need to know how to ask for directions to get where you want to go. These initial commands are your map and your compass. They allow you to not just move through the Linux environment, but to truly understand the terrain you're navigating.
So what are some of those first key landmarks or terms we need to know?
Okay, let's start with some key introductory terms.
Mm.
First, there are binaries. Now, these are simply executable files programs the computer can actually run. Think of them like .exe files in Windows. In Linux, you'll often find them residing in directories like uspin or usbin. Examples include common utilities you'll use constantly, things like ipsfes for checking process status, cat for viewing file contents, els for listing directory contents, and ifconfig for network interface configuration.
Okay, the basic tool.
Right. And even powerful hacking tools like air cracking for wireless hacking and Snort, which is an intrusion detection system, are technically binaries. They're executable programs. Next up, every user in Linux has their own home directory. This is typically the default location where any files you create will be saved. It acts as your personal workspace within the system. And of course, we've already introduced Kali Linux itself, that specialized distribution designed for penetration testing, preloaded with hundreds of tools. And again, the source references Kali 2018.2.
Right. And you mentioned the root user earlier. That sounds important.
Extremely important. The root user. Think of the Linux system like a big apartment building. There's the directory, which we'll get to, that's the very foundation, the ground floor from which all other floors and rooms the directories are built. The root user, on the other hand, is the building manager. They have the master key, they have full access to every single room, and they have the power to change the building's very structure if needed.
The super user.
Exactly. This root account is described as all-powerful. It's designed for a trusted individual who can perform almost any action on the system. Things like reconfiguring the entire system, adding new users, changing passwords. As a hacker or penetration tester, you will frequently find yourself needing to use the root account, simply because many specialized tools won't even function without those root privileges. They need that unrestricted access.
Okay, so the root user is the ultimate gatekeeper, you could say. And the terminal seems like the gate itself. Can you elaborate a bit more on the Linux terminal and what it means to be working in a shell?
Absolutely. The terminal is essentially your window into the command line environment.
Mm.
More formally, this environment is known as the shell. This is where you interact directly with the underlying operating system by typing commands, and crucially, it's also where you write and execute scripts for automation. Now, Linux actually supports many different shell environments, but Bash, B-A-S-H, is by far the most popular and serves as the default shell in Kali and many other Linux distributions. It's your primary interface for that deep interaction. And just as a quick example, a basic utility you'd use right there in the terminal is the password command. That lets you change a user's password. Simple, but fundamental.
And you mentioned the file system structure earlier, the directory. How is that different from Windows?
Right, understanding the Linux file system structure is also fundamental, because it's quite different from what you might be used to if you're coming from Windows. Linux doesn't rely on physical drive letters like C or D at the base of its file system. Instead, it employs a single, unified, logical file system that starts at grep. This single forward slash is often referred to as the root of the file system. Think of it like an upside-down tree, with the root at the very top and all other directories branching downwards from there.
Okay, so it's for the file system root, distinct from the root user account. That could be confusing initially.
It definitely can be at first. You just have to remember. Root user is the super administrator account, is the top-level directory of the entire file system. Now, you can always find out your current location within this file system tree by using the pwd command. That stands for present working directory. For instance, if you've just logged in as the root user, typing pwd will typically return root, indicating you're in the root user's personal home directory.
And how do you check which user you are?
Good question. To quickly check which user you are currently logged in as, you just use the whomi command. Simple as that. And for hackers, as we mentioned, you'll usually find yourself logged in as root because so many privileged operations and specialized tools require that all-powerful super user access.
Okay, so we're learning the landscape. We know how to find out where we are, pwd, and who we are, whomi. Once you know where you are, you obviously need to know how to move around. What are the essential navigation commands to get from place to place in the Linux file system?
That's the next critical step, absolutely. To change directories from the terminal, the command you need is cd, which is short for change directory. For example, typing cd etc. will take you directly into the etc. directory. This is a really important directory, commonly used to store system-wide configuration files. You'll often notice your terminal prompt actually changes to reflect your new location after you use cd.
Okay, so cd followed by the path. What about moving back up?
Right. To move up one level in the file structure, so moving back towards the root directory, You use cd, that's etcd times cd, that's cd space ... And if you want to jump directly to the very root of the file system, the absolute top-level key from anywhere you happen to be, you simply use cd.
CD, etc. CD, CD. Got it. Now, once you're in a directory, how do you see what's actually there?
Perfect question. To list its contents, meaning to see the files and any subdirectories within the directory you're currently in, you use the ls command. Lst -s. This is very similar, analogous really, to the jar command you might know from Windows or DOS. When you run ls, you'll typically see output showing names like bin, etc., home, root, var. These represent common top-level directories or files within that location. It gives you an immediate overview of what's available right where you are.
Okay, that helps with getting around and seeing what's there, but what if you're looking for something specific, like a particular file or a program, and you don't know exactly where it might be hiding in that big file system tree? How do you actually search for information within Linux?
This is where Linux really shines, offering several powerful search utilities, each suited for slightly different tasks. For general searching, especially when you need flexibility and power, the find command is your ultimate Swiss Army knife. It allows you to start a search in any directory you specify you can start from to search everything, or a specific directory like home, and it lets you look for a vast number of parameters, way beyond just the file name.
Like what kind of parameters?
You can search by creation or modification date, by the file's owner, by its group, by its permissions, even by its size. It's incredibly flexible. For example, a command like find, etc., type ff name Apache2, would start searching in the etc. directory. Look specifically for files, db type F, and find any whose name's exactly Apache2.
Okay.
Now, it's important to remember that find typically looks for exact matches by default, so you'll often need to use wildcards, things like the asterisk to match anything, the question mark to match a single character, or square brackets to match a range of characters. These help you handle non-exact matches, like finding apache2.conf when you just search for Apache2.
Makes sense. Wildcards are common. What about viewing files or filtering content?
Right. Once you've found a file, or if you just want to look inside one you already know, the cat command is incredibly versatile. CAT, short for concatenate. Simply typing cat filename will display the entire contents of that file directly in your terminal window, useful for quick peeks.
Okay.
But cat can also be used to create or overwrite a file. If you use cat filename, that's a single greater than sign, the redirect symbol, it puts cat into an interactive mode. Your prompt disappears, you type whatever content you want, and then you press cd2lladd to save and exit. Be careful, though. Using cat on an existing file will completely wipe out its previous contents.
Ah, okay, good warning. So overwrites, how do you add to a file?
Excellent question.
Oh.
If you want to add or append more content to an existing file without overwriting what's already there, you use cat filename. See the double greater than sign. That tells cat to append instead of overwrite. This is critical for tasks like adding entries to log files or modifying configuration files safely.
Okay, cat overwrites, cat appends. Got it.
What about filtering text? You mentioned finding specific lines earlier.
Yes, for filtering text, grep is a very powerful and truly essential command. It stands for Global Regular Expression Print, which sounds complicated, but its primary function is straightforward. Find lines within a file or stream of text that contain occurrences of a specific keyword or phrase. You'll often use grep in conjunction with other commands through a concept called piping, which is represented by the vertical bar symbol. Piping takes the output of one command and feeds it directly as input to the next command in the sequence.
Okay, like chaining commands together.
Exactly. For instance, catsnort.com grep output. This first uses cat to display the entire content of the snort.com file, but instead of showing it on the screen, the pipe sends all that text directly to the grep command. Grep then filters that incoming text, showing only the lines that contain the word output. This technique can genuinely save you hours of searching through massive log files or complex configuration files. It's incredibly efficient. Wow. Okay, grep sounds indispensable. Any other basic file management commands we should know?
Just a couple more essentials for now.
Yeah.
For creating new directories, the command is simply maer followed by the directory name you want, like M8 or MyScripts, short for make directory. Yeah. And to copy files, we use the cp command, short for copy. This creates a duplicate of a file, leaving the original file untouched. So a command like cp oldreport.txt home user documents new report final.txt would copy the file oldreport.txt into the documents directory and rename the copy to new report final.txt all in one go.
Okay, MEERNCP. That covers a lot of ground for basic navigation and file handling. What stands out to you most about how these foundational commands equip someone to interact with the system? It really does feel like being handed that detailed map and a powerful magnifying glass for everything inside.
To me, it's the sheer combination of precision and efficiency that these commands offer. These aren't just commands, they form a language that allows you to surgically interact with, observe, and manage the inner workings of the Linux operating system. You move beyond just, clicking icons and launching applications to truly understanding the data flow, the relationships between files, the logic behind configurations. It transforms what could easily be an overwhelming mass of digital information into something navigable, something comprehensible. And I think this level of intimacy with the operating system is precisely what differentiates a casual user from someone who can truly master it for any purpose, whether that's system administration, cybersecurity, or software development. It's about deep understanding through direct interaction.
Okay, we've successfully navigated the file system, looked inside files, created things, copied things. Now let's turn our attention to how you analyze and manage networks and even install new software, getting into the really practical applications that start to show Linux's power in a much more tangible way.
Exactly. This is where you truly start to leverage Linux's deep control for both uh, reconnaissance, figuring out what's out there, and system manipulation. These are absolutely critical skills in any technical field, but especially in cybersecurity. Understanding how to manage your network interfaces, how to potentially spoof your identity, or even redirect network traffic, along with knowing how to efficiently add or remove the software tools you need, fundamentally empowers you to configure the system precisely for the task at hand.
So where do we start with analyzing and managing networks?
A fundamental starting point is the ifconfig command. It's one of the most basic yet essential tools for examining and interacting with your active network interfaces. By simply typing ifconfig in the terminal, you query your active network connections. It displays crucial information like your current IP address, the broadcast address for your network segment, the net mask, and even the physical hardware MS address of your network card, often labeled HWIDR.
So it gives you a quick snapshot of your network identity.
Precisely. An immediate snapshot of your network presence. And building directly on that, MSE address spoofing is a very practical and sometimes necessary application of ifconfig. You can literally change that hardware address, the HWIDR, to mask your system's identity on the local network.
How does that work?
The steps are surprisingly straightforward. First, you need to take the network interface down, temporarily disable it, using a command like ifconfig if0 down, assuming if0 is your interface name. Then you set the new spoot MSE address using ifconfig if2ther 00.11.22.33.44.55, replacing those numbers with the desired fake address. And finally, you bring the interface back up with ifconfig ithrow up. You can then run isconfig again to confirm the change took effect. This ability to quickly alter your digital fingerprint on the network is, well, quite powerful.
Definitely sounds like it. What about higher level network manipulation like DNS?
Right, domain name system, DNS manipulation is another key area.
Yeah.
DNS, is that critical component of the internet. It's the system responsible for translating human-readable domain names like hackers-arise.com or google.com into the numerical IP addresses that computers actually use to connect. Now, a powerful and potentially abusive technique involves manipulating a specific file on your local Linux system, the echosts file.
The hosts file. I heard of that.
Yes. This simple text file provides a potent capability to essentially redirect traffic on your local machine, or even sometimes your local area network, LAN, to a specific IP address. You do this by manually creating mappings between domain names and IP addresses right in that file.
Right.
For instance, imagine adding a line like 192.168.181.131 bankofamerica.com to your echosts file.
Okay.
What happens then is any traffic originating from your system that's intended for the real bankofamerica.com would instead be sent to the local web server running at the IP address 192.168.181.131.
Wow, so you could intercept traffic locally.
Potentially, yes. This exact technique is leveraged by various hacking tools like DNSpoof and Ettercap for man-in-the-middle attacks, showcasing its practical and often malicious utility. It hijacks the very first step of connecting to a website.
That's incredible control over network identity and routing right on your own machine. Beyond networking, though, just being able to add and remove software efficiently seems like a fundamental skill for any OS user. How does Linux handle this, and what are the main commands involved?
You're absolutely right. Adding and removing software is a fundamental task on any operating system, And Linux, particularly distributions based on Debian like Kali or Ubuntu, provides robust tools for it, primarily through the App System Advanced Package tool. For searching for packages, let's say you want to install the Snort intrusion detection system, but you're not sure of the exact package name. You'd use apt-cache search snort. This command queries the system's list of available software packages, its repositories, and shows you packages related to your search term.
Okay, so apt-cache search finds it. How do you install it?
Once you've identified the correct package name, let's say it's just snort, installing software is done with the command apt-get install package name. So in this case, apt-get install snort. The system will then figure out any dependencies, other packages. Snort needs to run, calculate the download size, ask for your confirmation, YCN, and then download and install everything automatically.
Simple enough. And removing software.
Just as simple. For removing software, you use apt-get remove package name. So apt-get remove snort. Additionally, there's a very useful command, apt-auto-remove. After you remove a package like snort, there might be dependencies that were installed only for snort and are no longer needed by anything else. Running apt-auto-remove automatically identifies and removes these unused dependencies, which helps keep your system streamlined and clean, preventing clutter.
That's handy. What about updates?
Good point. It's important to distinguish between updating and upgrading packages. They sound similar but do different things. apt-get update is the command you run first. It doesn't actually install anything new. Instead, it contacts the software repositories defined on your system and downloads the latest lists of available packages and their versions. It basically refreshes your system's catalog of what can be installed or upgraded.
Okay, so update refreshes the list.
Right. Then apt-get upgrade is the command that actually upgrades the packages already installed on your system to their newest available versions based on the list you just updated.
Got it. Update the list, then upgrade the software.
Exactly. Now, for some software, especially maybe newer hacking tools or very specific applications, they might not be available in the standard system repositories. In those cases, you might end up cloning them directly from GitHub using the git command and then compiling or installing them manually. But apt handles the vast majority of common software installations.
This all sounds like a powerful toolkit for managing the system's software library. But you mentioned Linux is a multi-user operating system. That implies you need ways to control who can access what files and directories, right? Permissions must be critical.
They absolutely are. Controlling file and directory permissions is a core security mechanism in Linux,
Right.
fundamental to its design as a multi-user OS. Because multiple users can be logged in and working simultaneously, Linux requires robust methods for securing file and directory access to prevent users from interfering with each other's work or accessing sensitive system files they shouldn't touch. Essentially, the root user, or the owner of a specific file, can grant different levels of access, specifically read, write, or execute permissions, to 3 distinct categories of users.
Okay, what are those categories?
First, there's the owner of the file, usually the user who created it. Second, there's the group associated with the file. Users can belong to groups, allowing shared access. And third, there's others, meaning everyone else on the system who isn't the owner and isn't in the group. This structured approach owner, group, others, is a necessity to avoid chaos and maintain security in a shared environment.
So how do you actually change those permissions?
To change permissions, you use the chmodis command, which stands for change mode. It's important to note that only the root user or the actual owner of the file can modify its permissions. Permissions can be set using a couple of different notations. One is numerical, octal notation. This uses numbers from 0 to 7 to represent combinations of read 4, write 2, and execute 1. For example, chmod 755 myscript.esh. Here, 7, 4, plus 2 plus 1, give the owner read, write, and execute. The first 5, 4 plus 0 plus 1, gives the group read and execute. The second 5 gives others read and execute.
Okay, that's the number way. What's the other?
The other is symbolic representation. This uses letters.u for user, owner, G for group, O for others, A for all. Then plus to add a permission, to remove it, and to set it exactly. And the permissions themselves are R for read, W for write, X for execute. So the equivalent of making a script executable for the owner might be chmodu plus X myscript.esh, or chmodu plus XO plus X hashcat.htstat adds execute permission for the user, owner, and for others. This granularity allows really precise control over exactly who can do what with any file or directory on the system.
That makes sense. Are there security concepts related to permissions that are particularly relevant in hacking or security?
Yes, definitely. In the realm of security, understanding privilege escalation techniques is critical, and some are directly tied to permissions. One such technique involves something called the SUI bit, SUID for set user ID. When the SUI bit is set on an executable file, It allows that file, when run by any user, to execute with the permissions of the file's owner rather than the user who actually ran it.
Wait, so if a file is owned by root and has the SUID bit,
Exactly. If a program owned by root has this bit set, a regular, unprivileged user could potentially run that program and, for the duration of that program's execution, gain temporary root privileges. This can be a major vulnerability if the program itself isn't carefully written. Similarly, there's the SGID bit, set group ID. When set on a file, it grants the running process the privileges of the file owner's group. When set on a directory, new files created inside inherit the directory's group ownership. These are slightly more advanced concepts, but absolutely fundamental for understanding how systems can be secured or, indeed, exploited through permission misconfigurations.
so thinking about this whole section, network control, software management, permissions, what does this all mean for you, the listener, someone who wants to understand systems deeply? It seems like these tools give you incredible agency, turning you from just a user into potentially a powerful system manager or analyst.
What it truly means, I think, is that you move from being simply a consumer of technology to becoming a controller, an architect, potentially an investigator of that technology. The granular control over network interfaces, the precise management of software packages, and the intricate handling of file permissions, these things transform you from just a passive observer into an active participant in how the system operates. You gain the ability to analyze system behavior, diagnose problems, and custom tailor a system's configuration and security posture to an extent that simply isn't possible with more restrictive operating systems. This agency, this control, is the foundation for advanced cybersecurity practices, robust system administration, and fundamentally a much deeper, more empowered mastery of the digital world around us.
Okay, we've covered the static elements of the system, things like files and configurations. We've looked at managing networks and software. Now let's explore the dynamic heartbeat of the system. The running processes, how the system remembers things like environment settings, and crucially, what it writes down about its activities and logs. This feels like where the truly sophisticated understanding comes in, moving beyond what's just sitting on the disk to what's actively happening in real time and being recorded.
Exactly. This layer of understanding allows for truly sophisticated control and analysis. Everything from optimizing resource usage by managing processes to potentially maintaining stealth by manipulating environment variables or cleaning up log entries. It's about managing the living, breathing aspects of the operating system as it runs.
So let's start with processes. What are they and how do we manage them?
Okay, process management. A process is, quite simply, an instance of a running program. Every application you launch, every background service, runs as one or more processes. The Linux kernel, which we mentioned is the inner core of the operating system that controls nearly everything, is responsible for managing these processes. It assigns a unique process ID, PID, sequentially to each new process as it starts up. And critically, when you're interacting with these processes using commands, the PID number is often more important and more reliable to use than the actual name of the process itself.
Okay, so PID is key. How do we see these processes?
The primary command for this is AES, which stands for process status. By default, just running Fs usually provides a one-time snapshot of processes that were invoked by your current user in the current terminal session. It's often a very short list.
So not very comprehensive.
Not usually. No. For a truly comprehensive view, you'll almost always use Ps with specific options, most commonly PO. This combination of options, A for all users, U for user-oriented format, X for processes without a controlling terminal, shows all processes currently running on the system, regardless of which user started them, including all the background system services. It provides a much more complete picture of what your system is actually doing at that moment.
That sounds like it could be a lot of output.
It can be, definitely on a busy system. That's why you often use the pipe symbol, again this time to send the output of PO into grep to filter for specific processes you're interested in. For instance, PO grep IMS console would sift through that potentially long list and show you only the lines related to the Metasploit console process, if it's running. Very useful for finding specific things.
Okay, so PO gives a snapshot. Is there a way to watch processes dynamically?
Yes, that's where the top command comes in. In contrast to BIPs giving you that single snapshot, top provides dynamic process monitoring. As the book says, top refreshes the list dynamically. By default, it updates every 3 seconds, and it typically orders the processes by their current resource usage, like the percentage of CPU, percent CPU, or memory, EAM, they're consuming. System administrators constantly use top to keep an eye on the system's health and identify any processes that might be hogging resources or behaving suspiciously. When top is running, it's interactive. You can press keys for help, H, or most importantly, press Q to quit and return to the command prompt.
Right. And if you do find a problematic or suspicious process using H or top, how do you stop it?
That's where the kill command comes into play.
Yeah.
If you identify a process that's misbehaving, frozen, or potentially malicious, the kill command allows you to attempt to stop it. You typically use kill followed by the PID number of the process you want to terminate. Now, kill doesn't just kill outright. It works by sending the target process a kill signal. Linux actually has 64 different signals, but you really only need to know a few key ones.
Okay, which ones are most common?
Well, there's SIGUP, signal 1, which often tells a process to hang up and reread its configuration files. SIGINT, signal 2, is the interrupt signal, like pressing Ctrl-C. SIGGUT, signal 3, tells it to quit and dump core memory. But the two most commonly used for stopping processes are SIGTERM, signal 15, and SIGKILL, signal 9. SIGTERM is the default signal sent by kill if you don't specify one. It's the polite request. Please terminate gracefully, save your work, and shut down. Like asking someone to leave a party politely.
And SIDKILL.
SIGKILL, signal 9, is the absolute kill signal, as the book calls it. It's not a request, it's an order. It tells the kernel to immediately terminate the process, no questions asked, and reclaim its resources, often sending its memory contents to DevNull, the digital black hole. This is more like forcibly removing someone from the party. Hackers often use top to pinpoint resource-consuming processes that might indicate monitoring software or malware, and then they might use kill -9 followed by the PID to eliminate those processes immediately and forcefully.
Okay, kill -9 for the forceful stop. So, processes are the active elements. What about how the system stores and manages information that influences its behavior, like settings? And how can you manipulate that for performance or even, as you mentioned, stealth?
This brings us to user environment variables, right?
Exactly. User environment variables are essentially configuration settings stored as key value pairs within your current working environment, or shell. They're always uppercase by convention, like path, home, user. These variables determine many aspects of how your Linux system looks, acts, and feels. They are crucial for system efficiency, for tailoring your environment to your preferences, and notably, they can sometimes be manipulated for stealth. They exist within your current shell session primarily.
How do you see these variables? The simplest way to view all your default environment variables is to use the end command. Just type env and hit enter. It will display variables like home, your home directory path, where the system looks for commands, and shell, your default shell. You can also modify these variables directly in your current session to suit your needs. For instance, the book mentions the hissize variable, which controls how many commands are saved in your shell's history. Setting hissize 0 will prevent the system from storing any command history for that session. This means your up and down arrow keys won't recall previous commands.
So that offers a form of stealth, hiding your commands.
It does, though it can certainly be inconvenient for normal interactive use if you rely on history recall.
How do you make these changes stick around if they're just for the current session?
Good question. It's important to understand how to make changes permanent, or at least have them affect subsequent processes you launch. When you change an environment variable directly, like hissize 0, that change is usually temporary and applies only to your current shell session. If you open a new terminal window, it won't have that change. To make changes that will be inherited by new forked child processes programs you launch from that shell, you need to use the export command before setting the variable. For example, export my variable some value. This marks the variable for export to child processes. Making changes truly permanent across reboots usually involves editing shell configuration files like Botchareich, but export handles it for the current session and its children.
Okay, export is key for making them inherited. You mentioned the path variable. Is there something special about that one?
Yes, there's a critical caution specifically regarding the path variable. A very common mistake for new Linux users is to accidentally replace the entire path variable instead of appending a new directory to it.
What happens if you do that?
Well, the path variable is a list of directories, separated by colons, where the shell looks for executable commands. If you just set path root no whacking tool, you're telling the system, only look for commands in this one specific directory and nowhere else.
Oh dear.
Yeah. Suddenly your system won't be able to find even basic commands like lcd or ps because you've effectively taken away its map to all the standard system tool directories like bin and ushturban. You get lots of command not found errors unless you type the full path to every single command.
So how should you add to the path?
You need to append or prepend to the existing path. The common way is something like export path, pathbot root no whacking tool. The path part includes the current value, the colon is the separator, and then you add your new directory. It's vital to always append or prepend to the path variable to retain access to all the critical system binary directories.
Okay, crucial tip there. Append, don't replace path. And finally, for this section, what about what the system records? Linux systems are constantly logging events, which sounds like a double-edged sword, useful for forensics and debugging, but potentially revealing for someone trying to stay hidden after accessing a system.
Precisely. The logging system is an integral part of Linux operation and security. Systems automatically log a vast array of events, logins, errors, service startups, network connections, you name it. For hackers or penetration testers, knowing where these logs are located is paramount. Why? So they could potentially be deleted or obscured after an operation to cover their tracks. For defenders, understanding logs is crucial for detecting intrusions. The main configuration file for the common rcslog logging utility is at tkiicislog.com staff. The book notes that this file is typically well documented with numerous comments, making it somewhat easier to understand its structure if you take the time to read it.
What kind of things does it configure?
Inside at crcslog.conf, there's a rules section. This is where you define what information gets logged, which programs or system facilities have their messages logged, the priority level required for a message to be logged, and crucially, where those logs are stored, which files. Understanding these rules allows an administrator to fine-tune logging or allows an attacker to pinpoint the locations of relevant logs, potentially alter logging priorities to reduce noise or hide specific events, or even disable certain logging rules altogether if they gain sufficient privileges.
And logs can get huge, right? How is that managed?
Yes, logs can grow very large very quickly on a busy system. Linux systems handle this using log rotation. Most systems have this set up automatically. It's typically handled by a scheduled task, a cron job, that employs the logrotate utility. You configure how logrotate behaves via its main configuration file at logrotate.conf and sometimes additional files in eclogrotate.d. Common settings you'll find at eclogrotate.conf include things like weekly, specifying the rotation frequency, rotate for, meaning keep the last 4 rotated log files, create, telling it to create a new empty log file after rotating the old one, and compress, which tells it to compress the old log files, often using gzip to save space, though this is sometimes commented out by default.
Can you change these settings?
Absolutely. You might change these settings based on your needs. For instance, you might need to retain logs for longer periods for compliance or forensic investigation purposes, or you might shorten the retention period or enable compression if you're running low on disk space. The man logrotate command provides excellent documentation on all the customization options.
Okay, understanding processes, variables, and logs seems essential for deep system control. What stands out to you here is this depth of control over the system's ongoing operations and even its memory, its record of those operations. It's truly a different paradigm from what most users are accustomed to with, say, Windows or Mac OS.
My immediate thought goes to the transition from just using a system to truly mastering its internal clockwork, its living state. Most users interact with an OS at a very high level, right? They see the applications, the graphical interface, but understanding process management, environment variables, and especially the intricacies of the logging system means you're operating at the very heartbeat of Linux. This depth of insight provides an almost surgical precision. Precision over resource allocation, over the user experience, and critically, over forensic analysis and operational security, FOPSEC. It genuinely moves beyond a black box experience where you don't know what's happening inside to one of potential complete transparency and profound control. It offers a fundamentally different, more intimate relationship with your technology.
Okay, we've covered the static elements, the dynamic elements like processes and logs. What's fascinating now is how the book moves from simply understanding the system to actively building tools for it. Scripting sounds like the ultimate power-up for anyone wanting to truly harness Linux.
It absolutely is. I mean, this is where you really transition from being just a user, even an informed user, to becoming a creator within the environment. Scripting allows you to custom tailor Linux to perform specific, often repetitive or complex tasks automatically. And that automation is a hallmark of any advanced operator, whether their goal is system administration, cybersecurity TDPs, tactics, techniques, and procedures, or software development.
So where do we start with scripting? Bash seems like the logical first step on Linux.
Yeah.
Yes, let's start with Bash scripting fundamentals. At its core, a script in this context is simply a text file containing a series of commands that the shell can execute sequentially. It's a program designed to automate tasks. The very first line of a typical bash script is #binbash. This is known as a shebang or hash bang. It's crucial because it tells the operating system which interpreter, in this case the bash shell, should be used to execute the commands within the script.
Okay, the shebang is essential. What are the basic building blocks inside a script?
Some core elements you'll use constantly include variables. These are like containers to store data within your script. For example, name occupy the web assigns the string occupy the web to the variable named name. You also need ways to get user input. The read command is often used for this, like read devup, enter your name, username. This prompts the user with the message and stores their typed response in the username variable. And then you need to display output back to the user, which is usually done with the echo command. For example, echo, hello, uLetterName, would print a greeting using the value stored in the username variable. Notice the $DOM.
Can you walk us through a very simple first script?
Sure. Your very first script could be incredibly simple. Create a file, maybe named Hello Hackers Arise, and inside it, just put .bash, #binbash.echo. Hacking is the most valuable skill set of the 21st century. That's it. Now, a crucial step after saving this file is that you need to give yourself execute permissions on it. You do this using the command we discussed earlier. Chmod 755 Hello Hackers Arise.
Right, chmod, to make it runnable.
Exactly. That chmod command makes the script file executable. You might even see its file name change color, offered to green, in your terminal listing to indicate it's executable. Now, to actually run the script, you navigate to the directory where you saved it and you type Hello Hackers Arise.
Why the bad at the beginning?
That is vital. It explicitly tells the shell to execute the script named Hello Hackers Arise that is located in the current directory. The dot represents the current directory. This prevents potential security issues or conflicts if there happens to be another command or script with the same name located somewhere else in your system's standard path. It ensures you run the specific script you intend to run right here.
Okay, that makes sense. Safety first. How about a slightly more complex example, maybe involving those variables and user input?
Okay, let's enhance it. Imagine a script called welcomescript.sh. Notice the .sh extension. It's just a convention, not strictly required, but it helps identify shell scripts. Inside welcomescript.sh, you might have .bash, #binbash.read-p. Enter your name, -name-vid, enter your name, read DB, which chapter are you on? Chapter.rist, enter your name. Echo, hello name, you're currently working on chapter, read DP. Enter your name, echo, keep up the great work. You'd save this, make it executable with your mod 755 welcomescript.sh, and then run it with welcomescript.sh. It would prompt you for your name and chapter, store those in variables, and then use Echo to print a personalized welcome message incorporating that input using the notation.
That clearly shows the interactivity. How does this translate to more practical, maybe security-related tasks?
Well, the book introduces building a simple network scanner as a real-world application, albeit a basic one. Instead of trying to scan the entire internet, it focuses on a much smaller task, scanning your local area network for hosts that have a specific port open, like port 3306, which is commonly used by the MySQL database service.
Okay, so targeting a specific service.
Right. Within the script, you'd use a command line network scanning tool like nmap. The command might look something like nmap-ec 192.168.1.024-p3306 devnull sog MySQL scan. Let's break that down quickly. Nmap is the tool. -t specifies a TCP connect scan. 192.168.024 is the target network range. -p3306 is the specific port. Devnull suppresses the normal verbose output of map, and -ug MySQL scan saves the results in a greppable format to a file named MySQL scan.
Okay.
Then the script will likely take that output file, MySQL scan, and pipe its contents to grep to filter out only the lines indicating open port, maybe saving those specific results to yet another file, like MySQL scanup and hosts. This demonstrates how scripting lets you combine existing powerful tools like nmap and grep to automate a specific reconnaissance task, making it efficient and repeatable. You could even enhance this script to take the network range and port number as user input, making it a more flexible custom tool.
That's a great introduction to bash scripting and its potential. But Python is also frequently mentioned almost in the same breath as Linux when talking about hacking tools. What makes Python so prominent in this space, and how does it fit into building custom tools?
Python's prominence in the hacking and cybersecurity community is absolutely well-deserved, and it stems from several factors. It's highly versatile, capable of everything from simple scripts to complex applications. It has a relatively gentle learning curve compared to languages like C or C++s, making it more accessible. And critically, it has a massive ecosystem of libraries and modules, many specifically useful for network programming, data manipulation, and interacting with web services, all essential for security tasks. Its widespread use is evident in many popular hacking tools written largely or entirely in Python. The book mentions examples like SquallMap for database injection testing and Scapy for crafting custom network packets.
How do you get started with Python and its packages on a Linux system like Kali?
For installation and package management, Python usually comes pre-installed on modern Linux distributions. The key tool you'll use for managing additional Python packages is pip. You might need to install pip itself first, often via a command like apt-get install python 3 pip, using Python 3 because Python 2 is now end of life. Once pip is installed, you can easily download and install thousands of third-party modules from the Python package index, PyPI, using a command like pip3 install package name. For example, pip3 install request would install a very popular module for making HTTP requests.
Okay, pip is the package manager. What are some fundamental concepts someone needs to grasp when starting with Python scripting, especially coming from maybe Bash?
Right, there are a few key Python concepts that are crucial. Firstly, and this trips up many beginners, indentation in Python is absolutely critical. It is not optional like in many other languages. Python uses indentation, spaces or tabs at the beginning of lines, to define code blocks, like what's inside a loop or an if statement. Inconsistent or incorrect indentation will lead to errors and prevent your script from running.
So whitespace matters significantly.
Tremendously. Secondly, variables are fundamental, just like in Bash, but Python's variable typing is dynamic. Variables are essentially names associated with values, and these values can be integers, real numbers, floats, strings of text, booleans, true-false, or more complex data structures like lists, ordered sequences, and dictionaries, key-value pairs. You typically just assign a value, like IP address equals 192.168.1.1. Python also has many useful built-in functions ready to use, like print for output, linen to get the length of something, open for file handling, range for loops, sorted for sorting, and type to check a variable's type. The official Python documentation is your best friend for discovering these.
And you mentioned modules.
Yes, modules are a huge part of Python's power, especially for hackers. Modules are essentially separate Python code files containing functions, classes, and variables that you can bring into your own script using the import statement, for example, import socket. This allows you to leverage pre-written code for complex tasks like network communication, cryptography, web scraping, and much more without having to write it all from scratch.
Okay, indentation, variables, functions, modules, anything else foundational?
Just briefly, Python supports object-oriented programming, OOP. This involves organizing code around objects, which are instances of classes. The book uses an analogy. You might have a car class, the blueprint, with specific objects like my BMW, your Audi, and Mercedes, each being an instance of the car class with its own attributes, color, model, but shared behaviors, start engine, drive. While you can write simple scripts without deep OOP knowledge, it's a core concept for larger Python applications.
That gives a good overview. How does this translate into building actual hacker tools, particularly network-related ones?
Okay, let's look at network communications in Python, which is central to many hacking tools. The book provides examples of building basic TCP clients and servers. To build a TCP client, often used for tasks like banner grabbing, you'd primarily use Python's built-in socket module.
Banner grabbing, what's that?
Banner grabbing is a simple reconnaissance technique. Many network services, like web servers, SSH servers, FTP servers, send out a welcome message or banner when you first connect to them. This banner often reveals the type and version of the software running on that port. So a banner-grabbing script connects to a target IP address and port and simply captures and displays whatever initial data the service sends back.
How would that look in Python?
A simple script, maybe called Hackers Arise as SSH banner grab.py, would start with import socket. Then it would create a socket object, maybe sock on socket. Then it would use s.connect 127.0.0.122 to connect to the SSH port, port 22 on the local machine, 127.0.0.1. After connecting, it would receive data using answer s/ev 1 receive up to 124 bytes. It would then print answer to display the banner, and finally s.close to close the connection cleanly. This shows how just a few lines of Python using the socket module can create a fundamental network interaction tool.
Okay, that's connecting out. What about listening for incoming connections?
You could also build a simple TCP listening script in Python, again using the socket module. This could act as a basic server or a listener for a reverse shell, for example. A script like tcplister.py might define variables for the IP address to listen on, TCP IP, the port number, TCP port, and a buffer size. It would then create a socket, use sbind, TCP IP, TCP port, to associate the socket with the specified address and port, and then slisten1 to start listening for one incoming connection. When a client connects, con addr accepts the connection, giving you a new socket object con to communicate with the client and the client's address addr. Often you'd then enter a loop, maybe while true, that continuously uses con.rescue buffer size to receive data from the client and potentially con.send data to send data back, like echoing it.
So Python makes both client and server-side network programming quite accessible. What about controlling the script's flow, loops and conditions?
Yes, Python uses standard control statements to manage the flow of execution, similar to other languages, but with that crucial indentation defining the blocks. The if statement allows for basic conditional execution, if condition dot does something. You can add elif, else, and else for more complex logic. The for loop is used for iterating over sequences, like items in a list or a range of numbers generated by range. For example, for I in range.print, it would print numbers 0 through 4. And Python has try except blocks. Their primary role is robust error handling. You try a block of code that might fail, and if it does raise a specific error, the except block catches it and handles it gracefully instead of crashing the script.
How is try except useful beyond just catching errors?
Well, the book points out its utility in decision-making during certain hacking tasks. For example, imagine trying to brute force a login. You could put the login attempt inside a try block. If the login fails, incorrect password, the library you're using might raise an exception. The except block can catch that specific exception, print a failed message, and then the loop continues to the next password. If the login succeeds, no exception is raised, the try block completes, and you can then break out of the loop. It uses error handling as a form of flow control.
That's clever. Can you give an example of a more complete hacking script using these concepts?
Sure, the book details building a practical FTP password cracker script, ftpcracker.py. It starts by importing the necessary library, import ftplib for interacting with FTP servers, and maybe sys for exiting. It then prompts the user for input, the FTP server's IP address, and the target username. Crucially, it asks for the path to password list. The user needs to provide a file containing potential passwords, one per line. The book mentions using locate word list in Kali to find common word list files already on the system.
Okay, so it needs a dictionary of passwords.
Yeah, exactly. The core of the script is then a loop that reads each password from the provided list file. Inside the loop, it uses a try except block. The try block attempts to log into the FTP server using the target username and the current password from the list, ftp.login, username, password. If the login is successful, the FTP server typically returns a 230 status code. The script checks for this success code, prints a success message revealing the correct password, and then cleanly exits using sys.exit.
And if the password is wrong?
If the password is wrong, the ftplib library will likely raise an exception. The except block catches this specific exception, e.g. except ftplib.errorperm, prints a message like still trying, and the loop simply continues to the next password in the list. The output the user sees would be a stream of still trying messages, hopefully followed by success. The password is correct password.
Wow, that ties together user input, file handling, looping, network interaction, ftplib, and error handling try except into a functional, though potentially ethically dubious, tool. So thinking about both Bash and Python scripting, what does this all mean? This ability to write your own tools, from simple automations to network sniffers and password crackers, it seems like it fundamentally transforms you from just a user into a truly proactive force in the digital realm.
It means precisely that. It really signifies the leap from merely understanding the gears of the system to being able to actually forge new ones yourself. When you can script effectively in Bash or Python, you're no longer limited solely to the tools that others have created for you. You gain the power to adapt existing tools, to customize solutions, and even to invent entirely new approaches to specific problems you encounter. This capability moves you beyond reactive troubleshooting or simple usage into the realm of proactive solution development. Whether your goal is automating tedious system checks as an administrator, building tailored reconnaissance tools as a penetration tester, or even crafting sophisticated exploits as a security researcher, it grants an unprecedented level of agency and truly unlocks your potential to shape and interact with digital systems at their deepest, most fundamental level. You become a creator, not just a consumer.
Okay, this next section feels like where we truly step into the world of practical hacking, understanding how common services work, how they can be used or abused, and, crucially, how to protect yourself or remain anonymous online. It's about the interplay between offense and defense using real-world services and techniques.
Precisely. This component really highlights how a deep, practical knowledge of common network services, alongside techniques for achieving obscurity or anonymity, are absolutely critical. And not just for offensive operations, but equally for building robust defensive security postures. It's about understanding the vulnerabilities inherent in everyday tools and the countermeasures available to mitigate those risks, which defines so much of the practical cybersecurity landscape we operate in today.
So let's dive into using and abusing services. Where does the book start?
A prime example it uses is OpenSSH, or Secure Shell. SSH is, of course, a fundamental tool for securely managing remote systems. It's used constantly by system administrators for legitimate remote access and server management.
But also by hackers.
Absolutely. It's used just as readily by hackers to maintain access and control over systems they've already compromised. It provides an encrypted channel for command execution. The source presents a pretty compelling, if slightly dramatic, example to illustrate this: building a Raspberry Pi. This involves taking a tiny Raspberry Pi computer, equipping it with a camera module, and configuring it for remote covert surveillance.
How would that setup work conceptually?
Well, the setup involves starting the SSH service on your own Kali system. Service start, so it can receive connections. Then you enable SSH on the Raspbian OS, which is the standard Linux distribution for Raspberry Pi. This is usually done through its configuration settings. You attach the camera module. After the Pi is booted and connected to the same network as your Kali machine, for simplicity in the example, you'd find the Pi's IP address using ifconfig on the Pi itself. Then from your Kali system, you could use the sush command to connect to the Pi's IP address, log in, and potentially run commands to capture images or video from the camera module, all remotely and securely over the SSH connection. It's a practical demonstration of how a standard, legitimate service like SSH can be repurposed for covert operations if physical access to plant the device is achieved.
Okay, that's SSH. What about databases? They store critical information.
Right. The book discusses MySQL and its common open-source fork, MariaDB. These are incredibly widely used database services, powering countless websites and applications. A significant security vulnerability highlighted is their common historical default configuration. Often, the administrative root user for the database itself would have an empty password after a fresh installation. The book strongly emphasizes the importance of changing this immediately for basic security hygiene.
And how do you interact with these databases?
You interact with them using SQL, structured query language. SQL is essentially an interpreted programming language specifically designed for managing and querying data stored in relational databases. Basic SQL commands allow you to explore a database once you're connected. For example, select user, host, password from mysql.user. Might, depending on permissions, list the database users, and potentially even their password hashes stored within the core MySQL database. Commands like show databases list all the databases on the server, and once you select a database, for example, use credit card numbers, show tables, would list the tables within it, like card numbers, potentially revealing the structure of sensitive information if the database security is weak.
What about PostgreSQL? Is that different?
PostgreSQL holds a particular importance for hackers, according to the source, primarily because it's the default database of the most widely used penetration testing and hacking framework, Metasploit. Metasploit uses a PostgreSQL database behind the scenes to store information about its modules, exploits payload scanners, the results of network scans, discovered vulnerabilities, compromised hosts, and collected credentials. So understanding how to start and interact with the PostgreSQL service PostgreSQL Start, is fundamental for effectively using a powerful tool like Metasploit, console. Within Metasploit itself, commands like msfdb initialize the database connection, and db status confirms that Metasploit is successfully connected and ready to use its PostgreSQL backend.
And briefly, Apache.
The book mentions Apache Web Server primarily to note that it's the most widely used web server globally, or at least was at the time of writing. This implies its common presence on target systems that a hacker might encounter, making knowledge of its configuration and potential vulnerabilities highly relevant.
Okay, that's a powerful overview of common services and some potential security angles. Now, let's pivot to the other side of that coin, becoming secure and anonymous online. If all this activity is happening and systems are logging things, how do you disappear or at least hide your tracks effectively?
This is a critical area, and one filled with nuance and trade-offs. The fundamental problem, as the book points out, is that the internet, by its very nature, tends to give us away. Our normal online activity is tracked via our public IP addresses, and our browsing habits are logged by ISPs and websites through DNS queries and HTTP requests.
So how do we fight that? What's the first line of defense for anonymity?
A primary tool discussed for enhancing anonymity is the Onion network, more commonly known as Tor. The way Tor works is quite ingenious. Instead of sending your internet traffic directly from you to the destination server over regular internet routers, Tor routes your packets through a volunteer-run network of over 7,000 routers around the world. It employs multi-layered encryption, like layers of an onion. Your data, the destination IP address, and your original sender IP address are all encrypted. At each hop through the Tor network, only one layer of encryption is peeled back, revealing just enough information for that relay node to know where to send the packet next. Critically, no single node knows both the original source and the final destination. This complex routing and layered encryption provides relative anonymity.
How do most people use Tor?
The easiest way is by installing and using the Tor browser. This is a modified version of Firefox specifically configured to route all its traffic through the Tor network. Using the Tor browser allows you to navigate the regular internet with enhanced anonymity and also provides access to the dark web websites that exist only within the Tor network and typically have addresses ending in .onion. The book does offer a caution here. The dark web can contain illegal and potentially offensive material, so users should exercise extreme caution.
Is Tor foolproof? Are there security concerns?
Definitely not foolproof. The book discusses how intelligence and spy services, like the NSA, view Tor as a potential national security threat because it can be used by criminals and terrorists. It explicitly states that Tor's anonymity has been broken before and likely will be again. How? Well, agencies like the NSA are known to run their own Tor exit nodes, the points where traffic leaves the Tor network for the regular internet. They also employ sophisticated techniques like traffic correlation, analyzing timing and volume patterns of traffic entering and leaving the Tor network to try and match users to destinations, even without breaking the encryption itself. So while Tor can be effective at obscuring your identity from commercial services like Google or advertisers, its effectiveness against determined state-level adversaries is considered limited.
Okay, Tor is one option, with caveats. What else? Proxies.
Yes, proxy servers offer another strategy for masking your IP address. The basic concept is that a proxy acts as an intermediate system, a middleman. Your internet traffic goes first to the proxy server. The proxy server then forwards your request to the final destination, but it does so using its own IP address, not yours. The response comes back to the proxy, which then forwards it to you. This effectively masks your originating IP from the destination server.
How do you use proxies in Linux?
A common utility mentioned is proxy chains. This tool allows you to force the network traffic of other applications, even those that don't natively support proxies, to go through one or more proxy servers. You configure proxy chains by editing its configuration file, typically at etcetcproxychains.com. Inside this file, you list the IP addresses and port numbers of the proxy servers you want to use. You can choose different chaining modes. Dynamic chain means traffic runs through all the listed proxies in order, but if one proxy is down, it skips it and moves to the next. Strict chain requires all proxies in the list to be online and reachable for the connection to work. There's also random chain, which chooses a random selection of proxies from your list for each connection, potentially enhancing anonymity further. You can specify the number of proxies in a random chain using Chainline.
Are there downsides to chaining proxies?
Yes, the main trade-off is performance. While dynamic or random chaining can enhance anonymity by making the path harder to trace, routing your traffic through multiple intermediaries significantly increases the latency, meaning slower speeds and response times. And there's a major limitation regarding trust. The owner of the proxy servers you use can see your real IP address and potentially log your traffic. If that proxy owner is pressured by law enforcement or decides to cooperate, your identity could be revealed. So like Tor, proxy anonymity is definitely not guaranteed.
Okay, Tor and proxies. What about VPNs? They seem very popular these days.
Yes, virtual private networks, VPNs, are described as an effective way to keep your web traffic relatively anonymous and secure. The concept is similar to a proxy in that you connect to an intermediary server, the VPN server, which then forwards your traffic to the internet using its own IP address. Crucially, however, a VPN establishes an encrypted tunnel between your device and the VPN server. This means all traffic flowing between you and the VPN server is encrypted, hiding your activity even from your own internet service provider, ISP.
What are the main benefits?
The primary benefits are enhanced privacy, hiding your IP and encrypting traffic, and the ability to bypass censorship or geo-restrictions. By connecting to a VPN server in a different country, you can potentially evade government-controlled content and information censors or access streaming services like Netflix as if you were physically located in that country.
Are there limitations to VPN anonymity too?
Yes. The major one is trust in the VPN provider. The VPN provider must know your real IP address in order to send the return traffic back to you. While reputable VPN providers claim to have no log policies, meaning they don't record your activity, you are ultimately trusting them to uphold that policy and to protect any minimal connection logs they might keep, like timestamps or bandwidth usage, from seizure by authorities. Access to these records, if they exist and are obtained, could potentially uncover your information. So again, anonymity is not an absolute guarantee even with a VPN.
So Tor, proxies, VPNs, all tools with trade-offs. The book also mentions private email.
Yes, briefly. It mentions Proton Mail as an example of a service often used for private, encrypted email communication, adding another layer for secure messaging.
Okay, that covers online presence and anonymity. Let's switch gears slightly to wireless networks. They're everywhere. How does Linux handle scanning and potentially cracking Wi-Fi?
Wireless networks are indeed pervasive, and Linux, especially Kali, provides a powerful suite of tools for interacting with them, often referred to as the air-cracking suite. First, let's cover some key wireless terms you'll encounter. An AP is an access point your typical Wi-Fi router. The ESID, Extended Service Set Identifier, is the human-readable name of the network that you see when you scan for Wi-Fi, like My Home Wi-Fi. This is often just called the SSID. The BSSA, Basic Service Set Identifier, is the unique hardware MSC address of the access point itself. Wi-Fi operates on different frequency channels like 1.6.11 in the US.
How do you see your wireless interface in Linux?
For basic wireless commands, ifconfig, or the newer ipaddr command, will show your network interfaces. A wireless interface is typically designated as WAN 0, WAN 1, etc. There's also the iconfig command, which is specifically designed for configuring wireless interfaces. Running iconfig displays key wireless-specific data like the Wi-Fi standard being used, for example, 802.101.8n, the ESI it's connected to, if any, its current mode, like managed, master, or monitor mode, transmit power, and association status.
How do you actually connect to a Wi-Fi network from the command line?
You can use Network Manager's command line tool, NMLII. The command would look something like nmli dev Wi-Fi connect your network SSID password.
Your password.
All right, that's connecting. What about the cracking aspect? How does that work conceptually? Now, for cracking Wi-Fi, specifically older WPOP2 protocols using PSK, pre-shared key, the process generally involves capturing a specific piece of data called a four-way handshake. This handshake occurs naturally when a legitimate client device connects or reconnects to the access point. The tool arrow dumping is crucial here. You first put your wireless card into monitor mode, using airmog start well on 0, which might create a new interface like Willenomen. Then you run arrow dumping Willenomen to scan the airwaves. Its output shows nearby networks, listing their BSSID, the AP's MC address, PWR, signal strength, ENC, encryption type like WPA2, hashtag data amount of traffic, CH channel, and SID network name. It also shows connected client MSC addresses associated with each AP.
What information do you need from that scan to attempt to crack?
To crack a specific wireless AP, the book lists the crucial information you need to gather: the MSC address of a client currently connected to the target AP, the MSC address BSSID of the target AP itself, the channel the AP is operating on, and importantly, a good password list, word list.
How do you capture the handshake and use the word list?
Conceptually, you'd use arrow dumping again, but this time focused on the specific target AP's channel at BSSID, telling it to write captured packets to a file. For example, arrow dump -c10 bsid 01.01.abcc.22.your capture file, Yulin Paman. You might need to use another tool, like airplaying, to send deauthentication packets to force a connected client to disconnect and then reconnect, triggering the capture of that crucial handshake. Once you have the handshake captured in your file, you use a tool like air cracking itself, providing it the capture file containing the handshake and your password list file. AirCrack will then rapidly try every password in your list against the captured handshake data. If the correct password is in your list, AirCracking will find it and display it. The effectiveness depends heavily on the quality of the password list and the strength of the actual Wi-Fi password.
That's a fascinating overview of the tools and techniques for interacting with services, managing anonymity, and dealing with wireless networks. What stands out to you most about this particular array of tools and techniques? It really feels like a comprehensive look at how digital presence is maintained, how it can be hidden, or even how it can be exploited.
What stands out most profoundly to me is the sheer interconnectedness and the duality of it all. You can't truly hope to be secure or effectively operate stealthily without deeply understanding the very mechanisms that allow for observation, tracking, and potential exploitation in the first place. These tools and concepts, SSH, databases, Tor, proxies, VPNs, wireless protocols, they aren't just for hackers in the malicious sense. They are fundamental components of the digital world, and understanding them is essential for anyone seeking genuine digital mastery. They provide the lens through which we can see how services actually operate under the hood, how identities are formed and tracked on a network, and how the very fabric of digital communication can be both strengthened for defense and, if one chooses that path, potentially unraveled for offense. It really forces you to take a holistic view of the digital ecosystem, where every single interaction leaves some kind of trace and every common service can potentially be an entry point, or, conversely, a critical point of defense.
And finally, we arrive at the absolute nitty-gritty, the core of the operating system itself, the kernel, how Linux interacts with physical hardware devices like storage, and the immense power of automating tasks through scheduling. This feels like where the truly sophisticated, deep understanding comes into play.
Precisely. Understanding these elements really elevates your comprehension to an entirely new level. It reveals both incredibly powerful capabilities for building resilient systems and, at the same time, exposes subtle but critical vulnerabilities that can be leveraged for strategic penetration or defense. This is truly the deepest dive into how Linux functions at its most fundamental core level.
Let's start right at the center then.
Yeah.
The Linux kernel and loadable kernel modules, LKMs. What role does the kernel play, and what are LKMs?
Okay, the kernel. As the book states, it's the inner core of the operating system that controls nearly everything. Think of it as the central brain, the ultimate manager, orchestrating all hardware interactions, process scheduling, memory management, everything. It operates in a protected mode, separate from user applications, for stability and security. Now, loadable kernel modules, LKMs, are described as a convenience feature, but a very important one. They allow system administrators, or the system itself, to add new functionality or drivers, like support for a new piece of hardware, a new file system type, or even new network protocols directly into the running kernel without needing to recompile the entire kernel from source code and reboot the system.
That sounds efficient, but you mentioned vulnerabilities. What are the security implications?
Yes, this convenience carries potentially critical security implications. LKMs represent a significant potential weakness because they execute with the full privileges of the kernel itself. Malicious hackers can exploit this. If they can somehow convince a system administrator to install a compromised device driver, disguised as a legitimate update perhaps, or if they gain root access and load their own module, that malicious LKM, often containing a rootkit or other types of listening devices, can operate undetected deep within the kernel. This essentially allows the hacker to take total control of the system and kernel, potentially hiding their processes, files, and network connections from standard monitoring tools. The source material is quite emphatic here, stating, "Understanding LKMs is absolutely key to being an effective Linux admin and being a very effective and stealthy hacker. It's a double-edged sword."
How can you interact with the kernel on these modules from the command line?
There are several commands for kernel interaction. Uname A is a common one to check the version of your currently running kernel. lsmod, list modules, will show you all the modules currently loaded into the kernel at that moment. Modinfo module name gives you detailed information about a specific kernel module, like its author, description, and any parameters it accepts. Commands like insmod and urmod allow you to explicitly insert or remove a kernel module, though these are often used more for debugging or specific cases. A more sophisticated command is modprobe. It's generally preferred for adding or removing modules because it intelligently handles any dependencies, meaning if the module you want to load requires another module to be loaded first, modprobe will usually figure that out and load the dependency automatically.
Okay, so LKMs are the kernel's way of extending itself, but also a potential high-privilege attack vector. Moving slightly outwards from the kernel, how does Linux organize and manage physical storage devices and the file systems built on them?
This is another area where Linux has a distinct philosophy. The core concept is that, as much as possible, each device on your system is represented by a file in the dev directory. Dev is short for devices. If you use ls to list the contents of the dev directory, you'll see a potentially long list of special files. Some names might be recognizable, like cdrum, often a symbolic link, cp, or td for terminals. Others will be more cryptic, like CSDA, STB1, NVE0, and 1P1, representing storage devices and their partitions, all treated as files you can potentially interact with, though usually not directly.
How does Linux represent the storage devices themselves, like hard drives or USB drives? You mentioned CDA.
Right. How Linux represents storage devices has evolved but follows a logical pattern. Instead of fixed drive letters like Windows, Linux uses these logical labels, the device files in dev, which are then attached or mounted onto specific points within the single unified file system tree that starts F. Historically, FD0 might have represented a floppy drive, and HGB represented older ID hard drives. Today, you'll most commonly see STIDA representing the first detected SIDA, SCSI, or often USB-attached storage device. STB would be the second, SDC the third, and so on. NVMe drives, which are becoming very common, often appear as something like NVE0 and 1.
And partitions, like splitting a drive.
Partitions, logically divided sections of a single physical drive, are represented by appending a number to the drive label. So the first partition on the first C drive would be STD01, the second partition would be Z02, the first partition on the second drive would be SDB1, and so forth. For NVMe drives, it's often NVE0N1P1, NVE0N1P2, etc., P for partition.
Are there specific commands to get information about these devices and manage them?
Yes, several useful ones. LSBLK, list block devices, is a great command. It provides comprehensive information about block devices, storage drives, and partitions in a nice tree format. Its output includes columns like MJ-MIN, major minor device numbers used internally by the kernel, RM indicates if it's a removable device, size, human readable size, type E, disk, part, room fruge, and crucially, the mount point. The mount point tells you where that specific device or partition is currently attached within your main file system tree. Your example is SD1 might be mounted at EN and SDB1 might be mounted at MediaSpit drive.
Okay, LSBLK gives the structure. What about usage?
For usage, the df command, disk free, is standard. Running df, often with the xnh option for human-readable sizes like dfh, provides basic information on any hard disks or mounted devices, including CD-DVD drives or flash drives. It primarily shows you how much space is being used and how much is available on each mounted file system. Very useful for checking disk space. There's also fsmich, file system check. This utility is used to check and repair errors or inconsistencies on storage device file systems. You typically run it on an unmounted partition, like ssmkey-diff is db1, attempts automatic repairs. It's like Windows check disk utility. And briefly, the book mentions DD. This is a powerful low-level disk duplicator command. It's capable of making a bit-by-bit physical copy of an entire device, including areas that might contain deleted files, making it useful for forensic imaging or creating exact backups, but also dangerous if used incorrectly. You could wipe the wrong drive.
That's a deep dive into the physical and logical storage layers. Finally, the ability to automate tasks to make the system run commands for you without constant human intervention sounds incredibly powerful, especially in server or security contexts. Tell us about essential scheduling skills in Linux.
This is where you truly harness Linux's power to work for you, 24/7. The primary tool for scheduling repetitive jobs is cron. Cron is a system daemon, a background process that runs constantly, checking for scheduled tasks to execute. You tell cron what to run and when by editing a configuration file called the cron tab. Each user typically has their own cron tab, and there's also a system-wide one. The cron tab file format is highly structured and initially looks a bit cryptic, but it's logical. Each line represents a scheduled job and has several fields specifying the time, followed by the command to run. The fields are m, hdom, moan, dow, user command.
Can you break that down? mhdom.
Sure. M is minute, 0:59. H is hour, 0:23, 24-hour clock. DOM is day of month, 131. MON is month 112, or names like Jan, Feb. DOW of day of week, 07, where both 0 and 7 usually represent Sunday, or names like MON 2. You can use an asterisk in any of these fields to mean if you're in the hour field means every hour. User specifies which user account the command should run as. This field is usually only present in the system-wide cron tab, etc. cron tab. And finally, command is the actual command or script you want to execute. So an example from the book, 32.1.5 root maze scanning script. This would run the script root maze scanning script as the root user at 2:30 a.m., 30 minutes past hour 2, every day of month. Every month, but only on days of week 1 through 5, Monday to Friday.
How do you actually edit your cron tab?
The standard way is to use the command cron tab E for edit. The first time you run this, it might prompt you to choose a text editor, like Nano, which is usually recommended for beginners. This opens your personal cron tab file in the editor. You add or modify your scheduled job lines, save the file, and exit the editor. Cron will automatically notice the changes. Alternatively, for system-wide jobs, an administrator might directly edit the cron tab file using a text editor like LeafPad or Nano.
Can you give some practical examples of scheduling?
Sure. Common scheduling examples include system backups. You might schedule a backup script to run in the middle of the night on the weekend, say 3:00 a.m. every Sunday, 0:30, to avoid impacting system performance during peak usage times. Running a custom script like that mysqlscanner.ash we discussed earlier, you could schedule it for daily operation, maybe every morning at 9 a.m., 009 your Hosser path to mysqlscanner.ash. Or, as the book suggests, for stealthier reconnaissance, you might schedule it for very specific low-traffic times, like weekends and at 2 a.m. when it's less likely that anyone is watching the network traffic, and perhaps only during specific months, like June through August, 026860 your Hosser path to script.ash.
Are there simpler ways to specify common times?
Yes. Crontab also offers convenient shortcuts or special strings as alternatives to the 5-time date fields for common schedules. These include at yearly or at annually, at monthly, at weekly, at daily, same as at midnight at noon, and at reboot, which runs the command once every time the system boots up. So instead of 00mart, you could just use it daily for a job that needs to run once a day at midnight.
Yeah.
Example, at midnight your bonds are passed to MySQLscanner.esh.
That's much easier to remember. Lastly, what about making sure essential services, not just scripts, start automatically when the system boots?
Right, starting services at boot up is crucial for system automation and reliability. On many systems, especially older Debian-based ones like the Kali version referenced, the update RCD command was used for this. Running update RCD service name defaults, yeah, the no update to RCD PostgreSQL defaults, would configure the system's initialization process, system vinit or similar, to ensure that the specified service, like PostgreSQL, automatically starts when your system boots up into its default run levels. Modern systems increasingly use systemed, which has its own command, system idle enable service name, to achieve the same goal. The book also briefly mentions a rudimentary graphical tool called HorConf, which might be available from the Kali repository, offering a basic GUI for managing which services start at boot time, although command line methods are generally more common and powerful.
Okay, this final section really brings everything together: how Linux operates at its deepest levels with the kernel, how physical devices connect and are managed, and crucially, how you can make the system work for you, automating tasks even when you're not physically present at the keyboard. It truly showcases this concept of digital autonomy and deep system control.
It absolutely does. This level of understanding really transcends mere usage. It delves into the foundational architecture of the Linux operating system itself. It reveals how every piece of hardware is integrated through device files and modules, how its core processes are managed and scheduled by the kernel, and ultimately how you can orchestrate complex tasks and services to run perpetually and often invisibly in the background. It's the ultimate expression of control within the digital realm, where the system becomes less of a tool you simply use and more of an extension of your will, capable of executing complex operations autonomously according to your design. This kind of deep knowledge is really what transforms an individual from a user into a true digital artisan, capable of building, managing, securing, or analyzing systems with profound expertise.
Wow. What a journey we've taken today. Seriously, from understanding why Linux is the undeniable foundation for so much of our digital world, navigating through its intricate file system, managing its ongoing processes and logs, all the way to actively building custom tools with scripting and ensuring your anonymity online. We've truly peeled back layer after layer.
And in doing so, I think we've seen how every single layer of Linux, from its open source kernel right up to its automated scheduling capabilities, offers these profound opportunities for both control and insight. This deep dive is hopefully giving you, the listener, a genuine shortcut to becoming truly well-informed about the essential skills needed for navigating our increasingly complex digital landscape. We aim to transform what might have seemed like dense technical information into actionable, understandable knowledge.
And as the source material, Linux Basics for Hackers, reminds us near the end, hacking is complex and there is no single way in, which is very true. But with the foundational knowledge we've unpacked today, that detailed understanding of Linux's design philosophy, its core commands, its common services, its security mechanisms, and its potential for automation, you're not just ready to understand the how of many technical operations, but you can really start to grasp the why behind them.
Yeah, and that deeper understanding, that why, raises a really important question, I think, for you, the listener, to maybe mull over as we finish up. With this kind of granular control over digital systems, now potentially at your fingertips, with the ability to automate complex tasks, with all these powerful tools available, how do we, as individuals and as a society, as responsible digital citizens, ensure that this powerful knowledge is channeled constructively? How do we ensure it's used primarily to build, to protect, and to innovate, rather than merely to exploit or disrupt? It's worth thinking about the profound implications of possessing this kind of knowledge and how it can empower you not just technically, but ethically, to shape your own digital future responsibly.